Okay, so this is an outline. So there's a little bit of measurement I think we want to finish. And I should also say there's one subject that I'm not talking about here because I thought I have talked about measurement enough. But there is one thing that I want you to read up on, and that is jointly measurable observables. Yeah? So when can two observables measure jointly, and what does this really mean? And when can they not? Yeah? So this hinges on the commutativity or not among such observables. Is that something you have heard about before? Nodding. Okay, very good then. So if you haven't heard about it, you find it in the Sakurai. Discusses it at the appropriate length. Good. Yeah, so joint measurement is something that we will need, and that's related to measurements of non-maximal of non-maximal rank. Oh, excuse me, measurements being other than rank 1, sorry. Yeah, we need these degenerate measurements, and correspondingly, we will have to talk about joint measurements. Okay, good. So unitary evolution we will talk about today, and then we will talk more about quantum states, basis expansions. I'm sure you know that. It's just useful to bring it up again very quickly. Mixed states, density operators, and entanglement. And then we make the transition to quantum information theory type stuff, quantum computation, and we talk about the no-cloning theorem and the teleportation protocol. Can you please raise your hand if you have heard of the no-cloning theorem already? Okay, I'd say this is about half the class. Good. Okay, so let's get started. Okay, so this is a recap. This is what we did last time. This is the measurement postulates and probably the most general way we are going to write them down here, even though we need more general forms. So what's not in them, let me say that first is measurement for mixed states, for states described by density operators. So we'll discuss today what density operators are, and then they have a minorly different formula. I mean, it's basically the same, it's a tiny little bit different. And you find that formulation of measurement in the homework assignment. So you have it right there. So maybe we don't need to review it again here in class. At any rate, this is the most general form of the measurement process that we have arrived at. So this is the Dirac projection postulate. Yeah, so states are updated according to this rule. So basically we take the state that we have at the input and apply a projector to it, and then we just take care of normalization of states. And then there is a certain probability with that event occurring, and that's given by the Born rule. Okay, so this is what we discussed last time, and we will use that formula, those two formulas, I'm sure. Good, so now here was the exercise that we didn't really get to last time, yesterday. So I thought maybe just to check up a little bit, so maybe we talk about it briefly. So this is the exercise. We start with the Bell state. Sorry, we haven't really talked about the tensor product yet, but maybe you know it anyway. It's a two-party state, and the first qubit is measured in the eigenbasis of x. So x component of spin is measured, and the outcome is +1. So what is the state after measurement? Any ideas how you would approach this problem? Okay, so maybe to help you a little bit. So we would have to identify the projector corresponding to this measurement. So we are measuring the spin x component of the first particle and get the positive eigenvalue. So can you construct the projector corresponding to this? Maybe I'm skipping over it. Maybe it's even a bit unfair because we haven't really talked about the tensor product yet. So maybe we go through the lecture, and at the end, if we still have time, then we come back to this, and then we see how you do that. Yeah, maybe let's do it that way. But I think this is an instructive exercise. Although unfortunately, we will answer it partially or pretty much completely during the lecture. But okay, yeah. Let's come back to it at the end if we have time. That's about measurement. So now let's move to something else. I mean, we have only covered part of evolutions in quantum mechanics. The thing that you learn at the start. I mean, in your first quantum mechanics course, what did you do? Probably the hydrogen atoms. Probably the first thing you ever did in quantum mechanics, I would imagine. So you write down the Schrödinger equation. First the time-dependent form, and then time-independent form, and then you apply it to the hydrogen atom. So this is a very important formula. The significance is that it's, that most of, I mean, apart from measurement, most of non-relativistic quantum mechanics rests on that formula. So it's a very important formula. But it does have a few limitations, namely the one already mentioned. So it does not include the effects of special relativity, and it does not describe measurements. Okay, but apart from that, this is all you need for quantum mechanics. Okay, so we write it in a slightly more general form here. So what you have here is the time, this is the state, quantum mechanical state, Hilbert space vector. You have the time derivative, some decoration, that's the left-hand side. On the right-hand side, you have the state vector multiplied by an operator. That operator is called the Hamiltonian or Hamilton operator, and that is your time-dependent Schrödinger equation, a slightly more general formulation. How these two formulations are related, that we'll have to talk about, but not right away. Good. So this is basically the form of the Schrödinger equation that we will use here. So, okay, so that's that. And so it turns out that all evolution that comes out of a Schrödinger equation has a certain property, and that property is called unitarity. And so let's define that. So here you have an evolution operator U, and what I mean by an evolution operator is simply that, so our state psi at a later time, well, I don't know, maps into another state, U psi at a later time. So this is a linear operator as we use them in quantum mechanics. So for example, let me just write a second line here of that type of update. So this unitary could be time dependent and act on an initial state at time 0. And then the whole thing would be called psi of t. Time. All the evolution is encoded in that time-dependent unitary. Okay, and so now unitary is not just linear. Unitary means a bit more than this, and that's written down here. So if you take the unitary multiplied from the left with its Hermitian adjoint, you get the identity. Likewise, if you take that unitary and multiply the Hermitian adjoint from the right, it also gives you the identity. And so that's a property. It's a property of unitarity, and it is important for us because of questions relating to conservation of probability. So we I don't know, when we measure some observable at a later time, so we are certain that one outcome will occur. We don't know which one, but one outcome will occur with certainty, and we want that property to be preserved over time. And unitarity gives us that. You probably have proven this at some point in your past, that all evolution that comes out of the Schrödinger equation is unitary. So let's talk about unitary evolution a little bit. I mean, it's the biggest formula in quantum mechanics, so we can't just deal with it in 5 minutes. We have at least to do an example. And so we can go back right to our situation we started with, the Stern-Galler experiment. So what we talked about here is what the field gradient did. So we had the field gradient, and it would kind of pull the particle with the spin. It would pull it in different directions depending on what the orientation of that spin was. But that's not all that's happening. So you don't only have a magnetic field gradient here, you also have a magnetic field itself. And the magnetic field itself also does something. Namely, what it does is it rotates the spin. You get spin precession from the very same Hamiltonian that also gave us the pull on the spins. Okay, so it's kind of the simplest Schrödinger equation that you can solve, and you've probably done it. Let's just recap it so that we have occasion to speak about unitary evolution a bit, yeah, to honor its significance. Okay, so the Hamiltonian, which you also remember from classical physics, yeah, from both classical and quantum physics, the Hamiltonian is the energy function of your system. It gives you the energy that the system has, and it's also the generator of the evolution. You have that also in classical mechanics. So classically, the energy function is minus the magnetic field times the magnetic moment. So the magnetic moment we recall is a property related to the spin. So it has a bunch of constants in them. You see them right here. Okay, so this is the classical equation, and the quantum equation is kind of the same, except now everything has operator status. So, so the magnetic field remains here, and the magnetic moment is now related to the spin of the particle. Yeah, and that's also here, and then magnetic moment and spin are related by a bunch of constants that stand here in the front. Okay, and now let's look at these quantities a little bit. So the magnetic field is vector, and so is the spin. But the spin is something more than a vector. It is a vector, yes, but it's also an operator. So the magnetic field is a vector of numbers. The spin is a vector of operators, x component, y component, z component. And so when you take the dot product, vector times vector gives you a scalar, but you retain the operator valuedness of the spin components. So written out, this is the operator that you get for the Hamiltonian here. Okay, we simplify this a little bit. So let's just assume that the magnetic field points in the z direction. So only that component here survives. And then the quantum mechanical Hamiltonian becomes this. Yeah? So essentially it's a z component of spin decorated with a bunch of constants. Okay, and just kind of to simplify the expression a little bit, we give this bunch of constants a name, such that our Hamiltonian becomes this, just kind of constant times z component of spin. Okay. Yeah. And then you get something like this. So our Schrödinger equation is now this. Now you can insert a resolution of the identity. Oh dear, basis expansions. We'll do this later, but you have done it anyway. So what you're getting is a matrix, a vector-valued linear differential equation with a matrix here and a wave function, components of the state vector in here. Fortunately, the matrix is already diagonal, so you don't need to diagonalize it. So you get two linear differential equations here, one for psi up and one for psi down. They separate, they are not mixed by that matrix. Okay, and it's kind of the first differential equation that you ever solved in your life. Yeah, so time derivative of a function is proportional to the function itself. You know that this gives you exponential functions, and because of these i's in there, you get an I in the exponent as well. Good. Okay, so now Yeah, I'm going over this quickly because I assume you've done it before. Yeah, so you can now assume a certain initial state. So we are saying the initial state is the state that points in the x direction, a state with positive eigenvalue of sigma x. Yeah, and then you see what happens over time is that these components are being rotated. And then if you work it out, what it means, now it's good that you chose your seats in the back. Yeah, so when as time goes by, if you look at it in the Bloch sphere, you know that the spin is rotating. The definition of unitarity. So when we discuss quantum computation in the circuit model, we will introduce gates. Quantum circuits consist of quantum gates, and they will all be unitary. So it's good to know, to recall the definition. Yeah, we will also talk about a bunch of two-level systems. So yeah. So these solutions that we have found here, they will come up again. So let me briefly talk about basis expansion. So quantum states can be described in various bases, and this is in fact where these wave functions come in. Yeah? So basically, when you have your first quantum mechanics course, you start with a wave function. You don't know about the notion of state yet. You discuss everything in terms of wave functions. So probably the first thing you ever look at is the wave function in position space. It's just some wiggling thing in your hydrogen atom or whatever. And then a little bit later, you realize that sometimes it's useful, and that probably comes around the time when you talk about the Heisenberg uncertainty relation, that it's maybe also useful to think about the wave function of momentum. Yeah? But these are different functions as functions, but they describe the same object. So in the language that we have arrived at now, we say that they describe the same quantum state. The same quantum state. And so if that is so, yeah, basically these two things, the position and momentum wave functions, they are the same object viewed through different lenses. So we have to maybe make this more concrete, what these wave functions really are relating to the state. So, well, they are, it turns out, and we will see why in a second, they are these inner products. Yeah? So I'm taking an inner product of my quantum state with all the position eigencats, and that gives me the position wave function. So as I vary the position here, yeah, the argument in the wave function varies. Good, and the same holds for momentum. Yeah, so the wave function in momentum is the inner product of our quantum state with a momentum eigenstate. And so this is the real thing. These wave functions are the real thing viewed through the lens of bases, namely position basis here, momentum basis over there. Okay, so that's the motivation why we talk about basis expansions, and then of course it's a convenient computational tool. So let's talk about that tool a little bit. So we consider some orthonormal basis. Orthonormality is all that we require for now, and it could be any orthonormal basis. It could be the eigenbasis of some observable. We don't specify, it could be any. And then we have a way to write the identity operator on that Hilbert space. We write it as a solution of states in that basis. Okay, and that property we will use momentarily. Okay, so now let's look into this a little bit. So let's see, this is how we use it. For the first time we use it, we'll use it in this fashion. So psi equals psi, obviously. We can insert here the identity operator and then change the brackets. Yeah, multiplication is associative. So this is how we had the bracket. Now we put the bracket like this. And you see what becomes of this state here. It is now the sum of our states in the individual bases with certain expansion coefficients. Yeah? And so now you see how the wave function comes in. So this is the expansion coefficients are the wave function. And that can be in any basis. It can be position, momentum, whatever you like. Similar thing holds for operators. Yeah, you insert a resolution of the identity to the left and to the right. And and so you find this representation for the observable itself with these entries, with these matrix entries. So the upshot of all of this is you can identify a quantum state with a column vector of coefficients. And likewise, you can identify an operator with a matrix. And furthermore, operator multiplication becomes matrix multiplication. I'm sure you know this, and it helps a lot with specific calculations. So, for example, if you want to calculate the eigenvalues of some operator, you choose a particular basis, you write the operator down as a matrix, and then you diagonalize it. Yeah? So that would be a fairly convenient way of getting at the eigenvalues. So that's a computationally useful thing. As the introductory example makes pretty clear, though, that the wave function and the state are not the same thing. And that's because the state is a basis-independent concept, and the wave function is a basis-dependent concept. And that's pretty clear. Wave function depends on which basis you choose to evaluate it. Yes?
So if the basis A corresponds to like some location basis or something, if the wave function is the location wave function we look at, what are the bases I and J that correspond for the operator?
Oh, thank you. That was intended to be the same basis. Yeah, so we just have two labels here. So we didn't want to confuse the labels. If you don't, if you don't like it, you could say you could label these basis states Bj and Bi to make maybe more clear that it is the same basis. You just have two distinct summation indices. And then about the first part of your question, is this position or momentum or what? It can be anything. So in infinite dimensional Hilbert spaces, it can be position, momentum. Finite dimensional, it will often be spin. Can be anything, doesn't matter.
So the ket vectors are our Hilbert space elements, right?
Yeah.
Okay. And that's some sort of expansion or development? Or?
Yeah. This is the basis expansion. Yeah. Yeah, so there was the idea here was to illustrate the relation between state vector and wave function. Yeah. And so I get my upbringing in quantum mechanics was, and I think maybe that hasn't changed all that much, that you learn about the wave function first. And then after going through it a second or third time, you arrive at the concept of the state vector, and then you almost ditch the wave function. You never talk about wave functions very much again. But still, it is useful to make the connection, how the state vector, the new notion, and the wave function, the old notion, are related. These are matrices that you will see very often. So this is an example of the operator expansion. So here is an example of choosing a particular basis, and this is a choice we will make very often. So this is about a spin 1/2 particle. Yeah? So it has two spin states, and we want to know what the components of spin are, like x, y, and z component. Okay, and they are h bar over 2. H bar is the unit of spin and angular momentum. We have a 1/2 here because it's a spin 1/2 particle. Yeah, and then we have the Pauli matrices sitting here. So in that basis, in the eigenbasis of the z component of spin, the spin components, Z and all the other ones, have this form in which the Pauli matrices appear. Yeah? So Pauli matrices are 2 by 2 matrices. They are Hermitian. Yeah, okay. And have eigenvalues plus minus 1. Yeah, and if they are distinctly anti-commute. So commutation relations among Pauli operators are very simple. Yeah, either commutation or anti-commutation, nothing else can happen. And that's also a fact that you'll get a lot of mileage out in this course. So there will be a lot of Pauli operators or Pauli matrices appearing. Not just for individual spin 1/2 particles, but also for multiple such particles. Yeah, okay. So it's also, this is a kind of the most important basis expansion for this course. Okay. Another topic that comes up in the context of basis expansions is expectation values. Expectation values versus eigenvalues. Yeah. So I just this is again a measurement thing, but I still wanted to mention it here now that we have talked about bases. So the upshot of this tiny derivation, so let me say this first, is that the expectation value of a quantity is a weighted average of the eigenvalues. And the weighing is provided by the probability of the corresponding eigenvalues occurring. So pretty intuitive notion of an averaging. Yeah? You have a probability of a certain eigenvalue occurring, you multiply with the eigenvalue, and that gives you the expected value. Okay, so let's do this quickly. Yeah, I mean, you can do it at home if you want to. I also believe that you've done it before. So that the upshot of the derivation is this thing. So this is the quantum mechanical expectation value that is defined like this. This is a definition, and you do a bunch of simple manipulations, and you arrive at this formula. So this formula makes intuitive sense. Yeah? As I said, it is a weighing of eigenvalues with the probabilities of those outcomes occurring. Good. So the reason I bring this up is because you need to differentiate expectation values from eigenvalues. Yeah? So eigenvalues is what comes up in individual experiments. And expectation values is what comes up if you make many repetitions. Yeah? So what eigenvalue you're going to get, you can in general not predict. I mean, quantum mechanics gives us no way of forecasting that. We have to live with what we get. We can predict the probability distribution, and therefore we can predict the expectation value. So this is what quantum mechanics gives us. Yeah, and therefore it's very important to tell these two apart. They are different things. Tensor product. So this is a part, maybe the exercise was a little bit unfair at the beginning, because we haven't talked about the tensor product yet, and so maybe talking about a Bell state before having introduced the tensor product, maybe it was a bit much. Okay, so let's introduce the tensor product. And so what is the tensor product for? So here we have a spin. We call that system A. And it has a certain quantum state. It's a spin state pointing in some direction. And we know how to describe this now for spin 1/2. And maybe you probably know how to describe larger spins as well, but it doesn't matter right now. Yeah? It has a particular state. Particle B is about the same. It's also a spin, same spin or different spin, also pointing in some direction. And now you have these two things in the world. You know how to describe them individually, but you want to describe them as a joint system. And the question is how you do that. So this guy lives in its own Hilbert space, and this is HA. This guy lives in its own Hilbert space, HB. And we will argue, or that's kind of the standard theory is that there is a Hilbert space for the joint system 2. We call this HAB, and this Hilbert space we now want to construct. Okay, so if we have a Hilbert space HA, then we sure find some basis of it. So let that be the basis elements alpha I, and the same for the Hilbert space HB. So we have a corresponding basis, and that's made of states beta j. Yeah? And the label j runs from 1 to the dimension of that space. Okay, and now that we have these two bases, we construct the new Hilbert space by first constructing a basis for that Hilbert space. And that is what we now use the two old bases for, BA and BB. And so what we do, and here's this funny symbol that now arises for the first time, a tensor product. So the basis states are now the tensor products of basis states in the individual Hilbert spaces. Okay, so what does a tensor product do here? It basically stacks these two states together. We could still measure all the observables on one of the systems or the other of the two systems. And so if you measure an observable over here, the presence of this other particle is then noticed. Okay, so this is how we construct. We use this tensor product with just a stacking together of the two vectors. We use it to construct the new basis. Okay, and with the new basis, we also have the new Hilbert space. An important thing has been cut. Well, I don't know important. Somewhat important, and that's the basis. The dimension of the new space. So do you know, suppose, this space over here has HA has a dimension dA, and HB has a dimension dB. Do you know what the dimension is of the joint Hilbert space? The product. Yeah, it's exactly. Yeah, and so that relates to something that we'll talk about later. Quantum speedup, hardness of classical simulation. So if you have n parties now, so you have the same particle n times, then the dimension will be the local dimension to the power n. And so that grows exponentially in n. So Hilbert space dimension get very large very quickly. So the Hilbert space is a vector space. So if you have the basis states, and you also have all linear combinations of the basis states. And under forming these linear combinations, the tensor product structure is not preserved. So, not generally preserved, depends on the coefficients. So there are states in the Hilbert space that have this product form, but not all of the states, in fact, most are not. So not all of the states are of tensor product form, and that even though you have a tensor product Hilbert space, not all states are of tensor product form, and that leads us to the notion of entanglement. Yeah, so it's an important notion. And the Bell state that came up in this little exercise at the beginning is an example of that. So here comes the definition. So entanglement doesn't need to be between two parties only, it can be between any number of particles. And so, a state is entangled if it is not the product of local states. Yeah, and the local states can vary. So a state is entangled only if this inequality holds whatever you put there. Good, and so that's maybe a bit of a dry definition, but it was hopefully motivated by the preceding discussion. So an example is that state that we saw before, or similar to what we saw before. This is the Bell state, or one of the four Bell states. Yeah, and you see in the Z basis, and we'll talk about the other bases later, the two particles, the spins, they are anti-aligned. So if one particle is pointing up, the other particle is pointing down, and the other way around. So if this particle is pointing up, this particle is pointing down. Okay, so you have these two alternatives in superposition. Okay, so this is a state that is entangled. You cannot write it into a tensor product form, whatever you put here. So that's maybe a nice exercise for you to prove. If we have time at the end of this class, maybe we can do that. Maybe you can think about ways of proving that this state cannot be written in that form. Okay, so let's keep an eye on that. Okay, so that is the definition of entanglement and an example for an entangled state. Two more things about entanglement. So physical ramifications. Why is it an interesting property at all? Okay, so unfortunately this is the solution of the initial exercise, but you still need to extract it because we are talking about something more general here. So, okay, so we have this state B11, the Bell state, and now we measure one of the particles. Say we measure the first particle in this basis. So you see that is a general superposition of up and down, and we know general superposition of up and down represents a spin pointing in some direction. So this is the first basis state, and then we have another basis state with different but related coefficients. So you have, instead of alpha, now you have beta star, a complex conjugated. Instead of beta, you have minus alpha star. And the reason that these coefficients are chosen such as they are chosen is that makes these two states orthogonal so that they can form an ONB, orthonormal basis. And in fact, physically what this means is that these two spin states, the corresponding spins, they point into opposite directions. Okay, and so now you can make a calculation, tiny calculation, so what becomes of this state when you measure in this basis. So there is two possibilities. You measure the plus outcome, which for us shall mean that we find this state for the measured particle, and you can get the other outcome, which means that you'll find that state for the measured particle. Okay, so that's that. You measure that particle, you project, you know what the state afterwards will be. But there is a funny thing here going on. In a way, you're not measuring only, even if you physically measure only that particle, you do something to the other particle as well. And that particle, its spin also becomes definitely oriented, and it has an orientation that's exactly opposite to the orientation of the first. And if you get the negative outcome, you still have the same property. The two particles point in opposite spin directions. It's just exchanged which particle is pointing where. But in either case, you get perfectly uncorrelated, perfectly anti-correlated. Okay, so this is the point. So regardless of which outcome we get in measuring the Bell state in that basis, not only the first spin will be projected, that's the particle we measure, so according to the Dirac projection postulate, no surprise it is projected, but the other particle will be projected too. And this particle can be on Earth, and that particle can be on the moon. And it's, according to quantum mechanics, this still happens. And Einstein called that spooky action at a distance. And so instantaneously, quantum mechanics says that, so when I project this particle by measurement, I project that other particle too. And regardless of the direction in which I measure, I will always find perfect anti-correlation. So that was the weird thing. That's what Einstein called spooky action at a distance. Other people call it steering. Yeah, steering is maybe the positive angle at this when you try to use this property for something. So maybe a question to you: is this in accordance with special relativity? Yes.
And the answer is no. But we derived this from equations where we explicitly stated that this is not in accordance with special relativity, so there's no reason to expect it.
Yeah, that is the case. Yes. But yeah, and so it's a good point. However, in this case, there isn't even a contradiction with special relativity. And maybe to see that, we can look at what the person, maybe let's make a drawing here. So we have a person on Earth and a person on the moon, and they both have, at the beginning of the protocol, they have a Bell state shared between them, and then the man on Earth, or whatever person on Earth, woman, whatever, anybody, measures their spin in a certain direction, and we will find the other spin pointing the opposite way after the measurement, immediately after. And yeah, and so, oh God, this time it's not mine. Okay, so we can continue. Fantastic. So the question is, who knows what at which point in time? Yeah. So suppose this person here wants to bet money on the measurement outcome, but the person on the Earth has done the measurement, and we know that the outcome is probabilistic. So a priori, there was a possibility that the spin will be pointing up with respect to that axis or pointing down. So the measurement has found that the state was pointing up rather than down. Okay, but only the person on Earth knows this at this moment. Yeah? The person on the moon does not. For the person on the moon, the outcome could have been down as well. And so, well, what the person on Earth can do is to send one bit over, namely the measurement outcome, and then taking into account the measurement outcome of the person on Earth, then the person on the moon can make a bet. Yeah? But before that classical information being sent, the person on the moon can't do better than random guessing. So there is no violation with special relativity, even if we didn't have it in our equations in the first place. And that's important for how reasonable quantum mechanics theory is. Yeah? So it does not lead to superluminal communication. Yeah, I think that's an important point maybe to make. So you see that this is the resolution of the initial question. So remember, the initial question was, you have a Bell state and you measure one particle in the X basis. And that was the question. So now with what you have here on the slide, what is the answer to that question?
I believe you have the best data where the particles were always perfectly correlated, so they will both be in the cluster.
Or you have a photographic memory. That's right. That's the Bell state we were assuming then. Both spins pointing up or both spins pointing down, positive relative phase between them. Now we're using another Bell state. Yeah? So we have spins pointing in opposite directions, negative relative phase between them. You can answer for either. Maybe if you want to use the slide here as it is, you answer for this Bell state. And then we talk about the other one.
Yeah, so then we just discussed, like, if we have, if we know the measurement of one, then the other will be an opposite one.
Yes, exactly. So this will be, for this Bell state over here, yeah, the first particle, as we said, is projected in the positive x eigenstate, and so the other particle will be projected into the negative x eigenstate. And for the Bell state on that first slide, it was actually different. So both spins would be pointing in the same positive x directions. Yeah. But the takeaway message already from that problem, and now you see it more clearly here, you're measuring one particle, but you're projecting the other one with it. Good. Yes?
Yeah, one question about the explanation before about the Earth and Moon thing.
Yeah.
So if both on the Earth and on the Moon, the persons are doing a measurement, and they will measure probably something that is not contradicting one to the other.
Yeah.
And they know beforehand at which time they will measure. Won't they get information about what the other person would have measured?
Yeah. Yes. I mean, yes, they would.
But that's still not a contradiction to.
Yeah. So let's make this explicit. So there is whatever basis you choose. So there we have a probability for, with respect to any basis, we have a probability for, I mean, direction of spin up, down. We have a probability of down, up. We have a probability of up, up. And we have a probability of down, down. Yeah, so these are the four measurement outcomes that can occur. Can you help me filling in this table? Yes, thank you, but I want to see other hands too. Yes, red shirt and mask.
So we said they're perfectly anticorrelated. So the anti-correlated spins are have probability 1.5 and the other 6.
Yeah, that's exactly right. So because they are perfectly anti-correlated, these probabilities have to be zero, as you said. The other things that you said were also correct. But maybe we can't argue that yet. Yeah. So why are they the same? So that's maybe requires more thought, but they are indeed the same. So these are the correct probabilities. So now, I mean, maybe it's a bit, yeah. So really, what we have here, the physical data, is these probabilities. Yeah, and whether the two parties measure at the same time or the second party measures later or earlier, that doesn't really matter. The probabilities will always be like that. Yeah? And so now how does this look from party one? Party one, say, measures up. Okay, so then there's two possibilities remaining, up, down, and up, up. So, but maybe party A knows what the initial state was and therefore knows these probabilities and says, okay, this cannot occur, so that must occur. So from their own spin pointing up, they can conclude the other spin must have been measured down or will be measured down. Yeah, but maybe that's a complication of the affair. So what is real are these joint probabilities, and what the temporal order of measurement is doesn't really matter. commuting operations, yeah? Compatible observables. So that's the Sakurai part. Good. Okay, are there further questions on this matter? Maybe I can say, so Einstein, I mean, he didn't stop criticizing it in this way. Yeah? Just saying spooky action at a distance, probably weird. Einstein also gave an argument against this way of building a theory. That's the now famous, not immediately famous, but now famous Einstein, Podolsky, and Rosen paper, at the end of which the three authors suggest hidden variable models. Yeah? So kind of alternative theories geared at explaining the same phenomenology. And these hidden variable models, for some time, they were thought to be equivalent to quantum mechanics. You can formulate it this way, you can formulate it that way if you really care. But later, by Bell and by others, they were ruled out. Yeah? So local hidden variable models or hidden variable models more generally, they don't cut it. They can't describe the quantum phenomenology, and that fact will come up later in this course. Yeah? So Einstein's remark will be fruitful for us in this course, even if today we don't agree with it. Yeah, and so now we have talked about entanglement at the phenomenological level. We have also given the definition. So let's add one more thing. We are looking for ways to quantify entanglement, and we call these entanglement measures or entanglement monotones. And basically anything is admissible that satisfies two criteria. So it's a function from our tensor product Hilbert space into the positive real numbers or non-negative real numbers. And so we require these two things. Namely, first, the monotone needs to be non-negative, or excuse me, it has to be 0 for all states that are not entangled. So this is the way a monotone shows us that the state we are looking at is not entangled. And for all entangled states, it is larger than 0. Okay. And then the second property is that our measure is non-increasing under local operation and classical communication. So that makes intuitive sense to require that. I mean, an entanglement measure is supposed to measure the non-local properties, and so if we change a system locally, it should not affect it, or at least it should not be able to generate entanglement. And also when we send along classical signals, that is nothing quantum at all. So it also shouldn't change the entanglement in our state. Yeah, or at least should not make it bigger. So anything you do can only decrease entanglement if anything. So, I mean, if you're doing local operations only and classical operations, they should not be able to increase your entanglement. Okay, so these are your two conditions that you impose on a reasonable measure. And that does not uniquely specify such entanglement measures. And, well, there is a zoo of them. Entanglement is a big research area. But I just want to mention that there is two entanglement measures that we will be looking at in this course. So the first, and that will be happen in the measurement-based part of this course, measurement-based quantum computation. So the first is the geometric entanglement, and let's parse this definition a little bit. So what we do here is we look at the overlap of the state in question with all unentangled states, or well, with one unentangled state over time, and then we compute the magnitude of this overlap, and then we try to we maximize, the definition says, this magnitude of overlap over all unentangled states. Yeah, so what this, yeah, and then we have a minus sign to make that measure positive or non-negative, and the logarithm so that it's an extensive quantity. Okay, so intuitively what this is about, you try to approximate an entangled state with an unentangled state. And that measure tells you how close you get. Yeah, so that's the thing. And proving that, proving this property for that measure is easy, but that it is non-increasing on a local operation in classical communication is not so easy. But at least the definition is reasonably easy to parse. Okay, and then there is an entanglement measure that is based on rank width. It's something that has to do with graphs. Let me not give you the definition here because it's much more complicated. But at any rate, there's another entanglement measure that we'll be using here in this course. So we want to talk about mixed states. And so the reason that is, so there's two motivations that I will give. So let's start with the first. So the reason is that we want to introduce normal, ordinary probability into quantum mechanics. So just to make this a little bit more tangible, what we want is to describe a coin flip, or a flipped coin, which landed somehow, so you know it will be 50% heads, 50% tails, you can't tell any better. And that's a typical probabilistic scenario. Maybe not the most important one that you want to describe in quantum mechanics, but you still want to be able to describe it. This and things like it. And so how do you do this? And the starting point is to generalize quantum states to ensembles of quantum states. And so now what is an ensemble of quantum states? It's still quantum states, but now not just only one, but many, and then corresponding probabilities. These are the probabilities with which these states occur. So you are imagining a source that is spitting out quantum states in a somewhat unreliable fashion. So the quantum state will be psi1 at some point and psi10 at a later point. And all these various states, they come out with certain probabilities. So that's an ensemble. And we can apply this idea to our unbiased coin. So we have two states in our ensemble, the coin showing heads, showing head, and we maybe represented by this state, if we like. That occurs with probability 1/2 for a fair coin. And we have the coin showing tails, and that's maybe this, when we may represent it like this, also appears with a probability of 1/2. Okay, so the idea of the coin, the flipped coin, we can capture. And then, of course, the ensembles may be larger, probabilities may differ. So we can basically represent any probability distribution that we want in this framework. So we have extended quantum mechanics in that way. The flip side is, ensemble is a little bit of a bulky notion. It doesn't look nice. And so that is what we want to do something about. And that leads us to density operator. And so all we really can predict in quantum mechanics are expectation values of observables. Okay, and so now we are in an ensemble situation, and we want to compute the expectation value of some observable given we are dealing with an ensemble. So then that expectation value is defined to be, and this is a kind of intuitively meaningful definition, as the weighted average of the expectation values with respect to the states in the ensemble. Yeah? So if you had one state from the ensemble all the time, that would be your expectation value, but now you have many such states, so you weigh them, these expectation values, with the corresponding probabilities of these states occurring. Yeah, so it's intuitively meaningful to define it this way. And now we are manipulating this expression. So, so this expression can be written like that. It's basically the cyclicity of trace. And then we finally observe that the trace is a linear functional, and so we can exchange the order of trace taking and this summation. Yeah, so we take these factors in the sum inside and the trace outside, and also the operator A is not in any way affected by the sum, so we can also take the sum past the A. Okay, and so this expression becomes that, okay? And that now motivates the definition of what we will call a density operator corresponding to the ensemble. And so the density operator is this thing now. Yeah, and with this is the definition now. And with this definition, the expectation value that we care about becomes this expression, trace over observable times density operator. And that holds for all observables. Yeah, so all observables, their expectation values will be computed with respect to that ensemble with this quantity, the density operator. So this is a motivation for defining this quantity. And this is a more general notion of quantum state than we previously had. Good. So all information about the expectation values, which is all there is, all we can predict, is in that object. So that's our object. Yeah, and so we're not gaining information, we're not losing any information, but we get a nicer object to deal with. So we can replace the ensemble by the density operator. It's a bigger thing to store on your computer, though. Yeah. Okay, so there's another motivation. I think that's also kind of important. So maybe I should do a little drawing here. There's a lot of text on this slide and no graphics. So, so let's say we have a system and we have an environment. I mean, the notion environment already implies that it is not under your control. So you have an interaction which you don't like to have, but it is there anyway. You can't do anything about it. But you can observe, that is measure. You can measure the system only. So that is all observables that you can really measure. They will be of this form. They will act trivially on the environment and only non-trivially on your system. And so suppose you now are interested in the expectation values of such observables. So then there's a little bit of algebra. Okay, but maybe it's not necessary to go through all of this right now, but you end up with a similar situation. So for the observables with this structure, the expectation value that you're interested in becomes an expression of the form that we saw in the previous motivation as well. So we have the non-trivial, so we have a trace over non-trivial part of the operator times density operator on that system. And so the density operator on the system is obtained by partial trace from the state of the joint system. So again, there's a way of going from a state on a larger Hilbert space to a density operator on a smaller Hilbert space, and from that thing, you can then compute all the expectation values or the expectation values of all the quantities you can measure. So again, it's in a certain sense a simplification. Okay, so this is the second scenario in which density matrices arise. Good. Questions? Not the case? Okay, so then let's go to the formal properties of density operators. Yeah. So whatever your density operator is, if it is valid, it has these properties here. And yeah, so it is Hermitian, and I think you can see this coming out from the previous slide. It has, previous two if you like, it has unit trace, that's properly normalized, and it is positive semi-definite. And that means you can take your density operator and sandwich it with the same state from the left and right. No matter what that state is, this sandwich will always be larger or equal to 0. Another way to say it is that your density operator is not permitted to have negative eigenvalues. Final thing to say about it, so it may occur that your density operator has a single non-zero eigenvalue, and if that is the case, then you call the state pure. When you have a pure state, you can represent it with a state vector. So using the density operator was really an overkill. But you can still represent it like that. And if you have fewer zero eigenvalues and more eigenvalues that are non-zero, then you call the state mixed. Yeah, and that's kind of the probabilistic thing. Yeah, 50-50 coin flip has this property. The density matrix will have two non-zero eigenvalues. Transition to quantum computation. So this ends the review of quantum mechanics. So this is basically the domain of standard quantum mechanics that we will need. And we are done. And so I have a bit of time left. So let us quickly make the transition. Let's talk about elementary things that relate the quantum mechanics that we just reviewed to quantum information things. So the first of these is the no-cloning theorem. So by cloning, I mean go to the library, you take the Sakurai with you, but you cannot borrow it for very long because your classmates also want it, so you copy it. No problem. You can copy the Sakurai as many times as you want. Copying, standard notion of information processing. So quantum mechanically, however, this does not work. And it's an elementary thing to see. Okay, so what you see here is a copying machine at a very abstract level. So what it is supposed to do is you feed it an unknown quantum state, and then you have another system sitting there, the system that you want to put the copy in of that state. So the map you want to realize is takes one copy of a state and a kind of a convertible particle, a raw particle, and it maps it to two copies of the state you care about. That would be the quantum version of copying the Sakurai. But yeah, that cannot be realized. There's no copying machine that realizes this transformation for all states in Hilbert space. Yeah, so this is a difference already between classical and quantum physics. And we want to prove this quickly because the proof isn't very hard, and also it illustrates kind of important principles of quantum mechanics. So what we will be using here is linearity of quantum mechanics. So we observe that unitary evolution is linear, and also measurement, remember the Dirac projection postulate, is linear up to a scalar. Yeah, so there is this normalization thing, but if we leave that out, the measurement is also a linear operation. Yeah, what I mean by this, so the image under such an operation of the sum of two states equals the sum of the images. Yeah, yeah, and then for multiples it's the same. Okay, so the proof is indirect. Yeah, so we start with the assertion that copying works and run this assumption into a contradiction. Just a ordinary indirect proof. Okay, so let's assume the copier works for the state 0. Okay, so then it takes this into that. Assume the copier works for the state 1. Then it takes this pair into that. Okay, and now we consider one more state. That's the state plus, and it's the equal weighted superposition of those. So these relations, by linearity of the operations we can perform, so the output of the copier on this state is already fixed by these relations. Yeah, so this state here, now we can apply the copying by linearity. We can apply the copying operation to either branch of this state separately. And so what we are getting is some constant and then this thing plus that thing. Yeah, 0, 0. By this relation, yeah, so The 0 portion of this gives 0, 0, and the 1 portion in this gives 1, 1. Yeah? And whatever constant we put here, this is not equal to plus tensor plus. Okay? So if the copying machine works on these two states, it must fail on this state. Yeah? So it cannot work for all states simultaneously. So this is the contradiction. So the assumption that copying works must be wrong. Okay, so this proof uses nothing but linearity of quantum mechanics, which doesn't mean that it was immediately found. Yeah? Just because it's simple in hindsight doesn't mean it was easy to see in the first place. It rather operated the other way around. So what was tried first was superluminal communication. So the idea was by the spooky action at a distance protocol to send information, which we have seen that it doesn't work. And so the idea was a little bit refined, and it was said, okay, we do a different protocol. We measure in the Z basis and in the X basis, or an X basis here. And so that information encodes a bit that we want to transmit. Because we know that depending on the basis that we choose, also that state will be projected along the Z-axis or X-axis. And then we copy that state. And when we have 100 copies, we can pretty reliably distinguish whether they are all pointing to X and all pointing in Z. So if the copying machine existed, then this would have led to superluminal communication, and people thought that was cool, and filed a patent and started building this thing. Yeah? So yeah, I just want to say, just because the proof was very simple, it wasn't easy to find. So people took a completely different route and found out the hard way. Okay, so there's one more thing. I mean, time is up, so I will talk about it in the next lecture, and that also makes sense. So the next thing that we'll discuss is a teleportation protocol. So let me just say quickly what the teleportation protocol does. It's also an information transmission task. So it takes a Bell state, it takes an unknown quantum state from the Earth to the moon, if you like, by investing entanglement and actually sending 2 classical bits of information. Okay? Next time I won't say much more. So this is a problem on 8-dimensional Hilbert space. So that can also be a homework assignment for you. Figure out, prove this protocol, show that it really works, and figure out what the correction operations are here, down here, depending on the classical bits that the receiver gets.